Hi, I'm Adam Hassler, and this is my final presentation for back of the envelope estimation in quantum mechanics. My presentation is on food system resilience and sustainability. Now that sounds like it's not really a quantum mechanics problem, but the idea here is that we can use a lot of the techniques from quantum mechanics estimation, including dimensional analysis and perturbation ideas, in order to make inferences about the food system and potentially about food system volatility. So we'll be starting with a hypothesis. Now this is not my hypothesis. This is a popular hypothesis that floats around, especially in circles like organic farmers, especially small scale farmers, who, as you'll see, make certain claims. I don't believe a lot of those claims are really backed up. And so what I wanted to do with this project is to explore whether or not those claims are true. And I wanted to test whether or not those claims are true using these estimation techniques. So I'm going to present that hypothesis and a little bit of the background, both about where I'm coming from on this and some of the things that inspired me. And just to note that in the spirit of this class, we will be using mostly variables in order to make these inferences. How are we able to use variables and just to do this? Are we able to look at whether or not something increases or decreases and the effect that it has on other variables in the system that describe the system? Are we able to look at ratios? Are we able to compare things with various different dimensions, sort of cancel out some of those dimensions in order to end up with something that describes the system accurately? So part of the power of this is that it gets us really, really far without having to do the enormous heavy lifting that is involved in gathering a lot of the data that would go into some of these equations. Now we're actually going to run through a simulation of this much later in the presentation, but I think the power of this is that we can see how the system would change if we change just a few of the variables, thereby saving us what is essentially the full-time job of somebody doing their dissertation, a postdoc working full-time, a consultant for a big consulting firm, who would have to come up with the specific data on this. So I think we can get pretty far, but we're going to test that out. So here's the hypothesis. Food system that favors small-scale farming is more resilient and sustainable than a system that favors factory farming and monoculture. Now, as I said, this isn't my hypothesis. This is sort of a widespread belief. Now, one of the people who makes this claim is the guy who literally wrote the book on small-scale farming. His name is Jean-Martin Fortier. He's a Quebecois farmer, and he has an extensive YouTube channel. Like I said, he wrote the book on this, and has done a lot to help small-scale farmers make a go of it and be successful. So I want to watch this video here in its entirety, and hopefully it kind of describes a little bit about his approach.
Hey folks, today on the channel I want to talk about climate change and farming and how they're linked together. And you know, we're mid-February here in Quebec, where it's usually super cold and it's in the 50s Fahrenheit, above 10 degrees Celsius. There's no snowpack, and it feels like spring already, which, you know, it's far from normal. And I don't think this is something that is like a one-off spin, because in the last 5 years, I've really noticed how just like the snow cover just isn't there anymore, even here. And, you know, cold temperatures, they just don't last. And for a lot of people, they could imagine, yeah, that's great for you because you can get to garden year-round without any problems. But that's really not how I see it, and that's what I want to talk about today. There's a lot of folks out there that are conspiracy theorists that don't believe in climate change. I think these people should get more educated because they don't know what's going on. And the science is there. It's telling us that the snow caps are melting, and it's inevitable. They're gonna melt in the next few years. And so that's gonna create a huge change. And the thing that I see that's gonna happen is big farming like it's used to being done now in the last 60, 70 years, monoculture using a lot of water, like big fields, fully mechanized with a lot of migrant workers picking these vegetables that we find at the superstore. This model is not going to be able to survive climate change because these fields of monocultured crop, they require too much water. And with the climate that is unstable, going from frost to super hot, going to super windy, tornado-like, to all these kind of variables, this climate that's always changing, which is the main result of climate change, these farms are not resilient. They're just not. And the answer to this won't be factory farms. The answer to climate change and food security is not factory farms. It's not hydroponic farms. It's not lettuce grown inside. The answer to this is more small farms, more diversified, ecological, resilient farms feeding communities. Tens of thousands, tens of millions of them everywhere, nurturing the soil, adapting to what's going on, and being the real guardians of food. And that's what the answer to climate change is, and no one is talking about that. It really bothers me that no one is saying this because these farms are already there. A lot of them are actually doing the work. A lot of them are finding it very difficult, and they could get more support. They could get more funding. They could get more customer base, a bigger customer base. So, and you just need to take it for somebody that's been in the midst of it for all these years. This is one answer. Small farms, small, local, diversified, ecological farms that are resilient to climate change. Multiply those. Make sure that we have a local food shed. Make sure that we have the guardians of their soil that are there to feed the communities. Factory farms, hydroponic farms are not the answer to the global food challenge that we're about to face.
It's powerful stuff.
Hey folks, today on the channel I want to talk about climate.
So why do I want to bring up a little bit about me? I want him to be right. But unfortunately, I'm also a scientist and a designer, which means I can't be satisfied with just the claim from somebody that I admire. I need a little bit more than that. And so my hope is with this, I can test this claim. And furthermore, that I can test this claim without having to do a year's worth of research on specific data, that maybe we can figure out some relationships between various different inputs and outputs in order to ascertain whether or not maybe he's right, at the very least. But I think we can get pretty far. So who am I? I'm currently a student in the master's program for applied physics at University of Massachusetts, Boston, with the anticipated graduation date of 2026. But in the past, I did some stuff that was very different. I have a bachelor's in international relations where I focused on development economics, and another bachelor's in history where I focused on intellectual history and specifically on discourse networks. And you'll see a lot of developmental economics and a lot of my interest in networks coming up here. And yes, I have worked on a farm for a long time. These are me with my egg hens last year. So one of my inspirations for this is called the Drake equation. The Drake equation was developed in the early 1960s and became the basis of the Search for Extraterrestrial Intelligence, or the SETI program. And the aim was to approximate how many civilizations were out there with whom we could possibly communicate. And that number is represented here by N. Now there are various different factors that go into this. And what's powerful about this is many of these factors are dimensionless. They are ratios, they are fractions. And so you have things here like the number of stars in our galaxy, the number of those stars that have planets, the number of those planets that could support life, the number of those life-giving planets that developed communication, and whether or not they have communication at the same time that we have communication. And so this actually got pretty far and remains one of the most powerful equations in astrophysics when discussing the topic of extraterrestrial intelligence. So what does that mean for us? Well, my hope is that I could come up with something similarly compelling for the food system. Now, again, one of the powers of something like estimation and applied physics, when applied to something like this, is we've got this incredibly complex topic, food systems. So complicated, so many interrelated factors. And that's where something like estimation or dimensional analysis is really powerful, because we can break things down into what are the most important factors of this. And that was my hope here. So moving on, I was really influenced by a theoretical physicist named Geoffrey West, who wrote a book called Scale. And it's about all of the ways that things get bigger and smaller, and the ways that design has to change in order to facilitate going bigger and smaller, and whether we can look at a small picture and whether or not that picture gives us insights into a much larger picture. So I looked at both geographical scale and time scale. So on a geographical scale, looked at 4 different ones: the global scale, a national scale, the US, regional scale, just the Northeast, New England and New York, and the Boston metropolitan area, which is where I live. So this is one of the few places, until we get to the very end, where I'm doing a simulation on this, where I actually used some hard numbers. On the y-axis here, you've got calories. Those are measured in quadrillions. Just bear with me on that one. And over here on the x-axis, you've got a year. So what are the lines here? The lines represent the nutritional requirements of each one of these systems, which is to say, a human being requires 2,000 calories per day to live, times 365 days in a year, times the population in the system. So you see a growing number of calories for the global system from 1975 to 2045, which is more or less my scope. You see a similar incline on the USA. See a much flatter incline on the Northeast, because as a region, we just aren't growing as quickly as other regions in the country. And then over here, Boston metro area, again, an incline. Now, one of the things that surprised me in looking at this, and as I said, these were hard numbers. They were actually, what occurred or the official numbers of what is projected. They're very linear. I didn't use a logarithmic scale or anything like this. And I think that that is owing to the relatively small time scale that we're looking at. We're only looking at 70 years here. Generally, one would expect sort of an exponential growth. I think owing to this very small time scale, it still looks rather linear. So important to know is this concept of superlinearity versus sublinearity. Now, these dots that I put on here are arbitrary. They don't represent an actual number. I put them on here in order to talk about these concepts. These dots that are above the line are called superlinear dots. These ones that are below the line are sublinear. So let's imagine that these dots represent the amount of food that is produced. So we've got this line, which we already discussed, which is the amount of food that is required. And then above this line, up until, it's like, I mapped it out until about 2015, we were producing more food than we needed. And then it starts going down here, we're producing less food than we need, which would require a correction in either way. Now this is a topic that is as old as time. You've got lean times, you've got boom times. Any civilization is, during a huge surplus of a crop, they'll put it away in storage, in anticipation of, maybe a poor harvest the following year or conflict, or being prepared for that sort of thing. However, this is crucial to understanding Jean-Martin Fortier's claim, is that if we continue on the trajectory that we are on, where there is an increase in factory farming and monoculture, fewer farms, growing acreage per each one of those farms, that we will be approaching sublinearity at best. However, if this sublinearity continues and we're no longer able to support our nutritional needs, then this growth will eventually hit a hard line and we're no longer able to grow anymore, and the system will collapse. We'll talk a little bit about that in a bit. Now, important too is this discussion about world hunger. I think that there are somewhat spurious claims being made, and I'll go as far to say that there are even myths about world hunger, which is that, we don't, these famine-ridden countries, they don't produce enough of food, we have to deal with this, famine and hunger problem. Meanwhile, when you look at the actual numbers, many of these countries that are experiencing famine are actually net exporters of food. And so many of the problems are less about how much food is being produced and more about problems related to supply and demand, supply chain and logistics, policy. Unfortunately, we can't get too into that here because this is a presentation about production. And while some of those things end up affecting production, and we'll talk about that, those have a major impact on whether or not these needs end up getting met. But here we can see how production would relate to nutritional requirements. So this is basically that statement, just put more concisely. The system will collapse if we continue on the trajectory that we're on. So here's where we get a little bit more of the physics. And luckily, it's not too far of a leap, because thinking about what most physics students are pretty familiar with, the Hamiltonian. The Hamiltonian is a description of the amount of energy that's in a system. While in a normal physics conversation, we would be talking in terms of joules. Here we're talking about a food system on various different scales, but we're still talking about energy. We're talking about the number of calories that are in the system. And also very familiar to most physics students is that in an equilibrium, you have this sort of base amount of energy, but then you've also got perturbations, which are potential energy changes that could influence that equilibrium energy both up and down. So let's define what that equilibrium looks like for a given system. Here's the most basic food system production equilibrium. Now we're looking at food system production here. So the calories per year equals the number of farms times the average number of acres per farm times productivity, which is the number of calories per acre. That is how much food is being produced in a food system. However, the food system is not only made up of food that is being produced, but we'll get to that in a moment. So number of farms. This is pretty straightforward, and this is actually an amount that is decreasing. But this could include smallholder farms, very large farms, include farms that are owned by families, farms that are owned by corporations. The range is enormous. But this is just a number of farms. So this is where we get into the dimensional analysis a little bit. So we've got farms on the table. Now we've got the average number of acres per farm. Number of acres divided by number of farms. So farms cancels out, we're just left with acres. Productivity, calories per acre. Acres cancels out, we're just left with calories. Now, this was number of calories per year, which means that is how much food is being produced in any given system. But the food systems on our planet, including each food system nationally, regionally, in a metropolitan area, we don't just produce all of our own food. We bring in food from other systems, and we send some of the food that we produce out. And many of these different food systems are completely different. So for example, the food system in California, they produce a lot of the food for the rest of the country. So this export number is huge, and they probably import very little. Meanwhile, you have somewhere like Alaska or Hawaii, where they have to import tons of their food because they don't actually produce the range of calories that they need. And so that's where you get sort of a $9 gallon of milk. So let's talk about perturbation and resilience. Over here on equilibrium, that's sort of our all things being equal amount. But all things aren't equal. Things happen, things change that end up affecting how much energy, how many calories are in the food system. So what is a perturbation? A perturbation, the units of a perturbation are also calories, but that perturbation could be calories that are increasing the amount of energy that's in the system, but more often than not, a perturbation is in reference to the number of calories leaving the system. So the equation that I came up with for figuring out the perturbation value is the inverse of the resilience, and we'll talk about what that is, times the total of the expectation value. An expectation value being likelihood that something's going to occur, right? So before we talk about resilience, I think it's important to talk about different network types. Our food system doesn't look like a social network. It actually looks more like a circulatory system. We've got arteries, we've got veins, and then down to the different consumers of food, those are the little capillaries. Those are the ends of the line. Now, we could think about this more circularly, that some of my food waste goes out to compost, but for the sake of this, let's think about the consumer as being the end of the line. So each one of these networks is measured by the number of nodes and the number of edges. The number of nodes are things like a farm, or a distributor, or a market, or a consumer, entities within the system. The number of edges are connections between those nodes. So you don't necessarily have bigger nodes or smaller nodes. What you do is you have more or less nodes and more or less edges. So moving on to resilience, I've created this resilience coefficient. So the resilience coefficient is made up of, it has to be normalized, so it's going to be between 0 and 1. And that's made up of the log of the number of nodes in the system that are farms divided by the log of the total number of food-related nodes in the system. So obviously, as there are fewer farms in the system, this number of farm nodes will go down, thereby affecting the resilience coefficient. This will change. This number will get smaller. And so if we take the inverse of that and multiply it by these expectation values, we get our perturbation. So what does this expectation value mean? We hear this kind of thing all the time. There's a 20% chance that in the next 5 years, the food system will be affected between X number of dollars and Y number of dollars, right? That's an expectation value. That's 20% times a range. But expectations work because you take the sum of all of those expectations has to be 1. So there's a 20% chance of that range, but that also implies that there's a 20% chance that it will be less than that. Or there's a 10% chance it will be more than that. So it ends up being a curve. Every one of these perturbations would end up having a curve for any given year, right? So if we add these perturbations to the equilibrium, we end up seeing that we have a nice, tidy equation here. But each one of these different scales will probably experience a different perturbation. So on the global scale, the types of perturbation we're going to see are climate change, which Fortier has talked about in his video. That doesn't just mean changes in temperature. It means more moisture in the air. It means changing seasons. Seasons will begin earlier or later. Seasons will end earlier or later. All of these things end up affecting the climate. Conflict, we see that right now with Ukraine. They're a major food producer, and so the conflict in Ukraine had a major impact on the number of calories that were in the food system globally. Pandemic, COVID had a massive impact on the food system globally, and that's measurable. Or economic shock. As it happens, if you look at the timescales I was using, exactly 50 years before now, there was a major economic shock when the US made a deal with the USSR for grain. The US gave a lot of our surplus grain, or signed a multi-year deal with the USSR to sell a lot of our surplus grain to the USSR. And it completely shocked the system. Prices spiked. A lot of people got into the wheat game who weren't in it before. People who were poor suddenly couldn't afford grain. So it speaks to some of those supply chain issues that I was talking about before, supply and demand, but it did end up affecting production as well. So what do we see in terms of the equation nationally? Again, we have the same equilibrium here, but now we have imports and exports. Obviously, there aren't imports and exports on a global level because we're not getting food from outside of the globe. But on a national level, we see lots of inputs and outputs. And in fact, the United States was known as sort of an agricultural powerhouse for a long time. And very recently, we suddenly become a net importer of food, which is a major shift for us. In addition, we see perturbations that occur on just a national level. Foodborne illness, we usually deal with that on national level, whether it's recalls of products, that kind of thing. The CDC handles a lot of that stuff. Subsidies and tariffs, that usually impacts how much food is being produced. We put a lot of money into corn, for example, and so a lot more corn is being produced than the market would probably allow for just on its own. But notice I included climate change here again, and we're going to see this on every scale. Climate change impacts food production on every global or every geographical scale. On a regional level, again, we see climate change, but now we see weather events. These weather events are very much specific to the geographical scale. Up here in New England, we might see, a lot of heavy rain because of our hurricane down in the southeast. Meanwhile, Florida, Georgia, Alabama, North Carolina, they are getting pummeled by hurricanes. Several in a season, far more than they used to. So these weather events, while region specific, they end up kind of being, at least initially, confined to this regional geographical scale. We can talk a little bit about how that ends up affecting the rest, the other systems, sort of parallel systems. And also invasive species, a very regional specific thing. What about the metropolitan area? We actually see far fewer metropolitan specific perturbations, but we're seeing food come in and food go out. Now, the Boston metropolitan area probably isn't exporting a whole lot of food. However, some of these variables are changing. We'll talk a little bit more about them in a second. Number of farms, number of acres per farm. those variables are changeable variables. They're not invariant. So let's talk about just what I was saying, the changes between these variables, and see if we can make a projection. Calories per acre, or productivity, is affected first and foremost by innovation. If we didn't have innovation, this is what calories would look like, right? It would go up and up and up, and as the population grows, it would end up hitting a limit at time equals time prime, right? This moment here is called the singularity. If we hit this singularity, the system collapses. However, we're still here, we're still eating, we're still buying food in the market. We don't have a lot of issues, at least not here in New England. Prices may change, we may see inflation go up and down, but all in all, we're still surviving. And that is thanks to innovation. What innovation does is it resets the clock. So instead of going up to a singularity at this point, it pushes it back. Now, innovation is Sisyphean in the sense that you roll the boulder up the hill, rolls back down, you have to quickly get back on the other side and roll it back up. That innovation has to keep coming, and it has to keep coming at faster and faster rates because you've just got a smaller and smaller push every time. What about food times average number of acres? Farms times the average number of acres per farm. This is changing. The number of farms, especially nationally, is going down, and the number of acres per farm is going up. Is that bad in and of itself? No, because one of the types of innovation that you see, we go back to this, these economies of scale. As farms get bigger, they are able to get a lot more from each one of their acres. You can get a big combine harvester, more mechanization. There's just more economies of scale possible. Also of note for the innovation stuff is you have technological innovation, which more and more is available to all different size farms, and technical innovation. We see the FDA do a lot of this. They do farm visits and teach people different tilling techniques or crop rotation techniques, that kind of thing. And this number of farms versus farm size, this actually has an impact on the metropolitan area too, because you see more urban farms, for example, small 2-acre plots in the middle of Detroit. So it's increasing the number of arable land in a particular area, which is going to have a big impact on the average number of acres. So increasing calories from external sources, this is actually a very big deal, because the more and more, thanks to a very neoliberal form of capitalism, the more and more interconnected we are, the more and more perturbations from outside of the system end up affecting our system. And that has to do with the proximity between me, the consumer, and where my food is coming from. And it also has to do with the severity of those perturbations elsewhere. And so 50 years ago, the fact that there was a conflict in Ukraine might not have had a big deal or a big impact on the food system in which the local food system in which I live. However, now that global conflict has a trickle-down effect across every other geographical scale. More and more and more this is true. And so that's where we're seeing this, is then the net import and export. And then, thanks to chaos, everything becomes unpredictable. We've actually never had something that we can think of as like a stable climate. Climate is always changing. And it is, in fact, people who are working in weather who first came up with this concept of chaos. And it's why we have these things called ensemble predictions, which allow us to sort of see an average across various different possibilities. However, the problem with chaos is it suddenly shifts a system from being linear to being very nonlinear, which means it becomes very unpredictable. And it is here, in chaos, that resilience becomes huge. Because something that might have been linear before now is changing. You know, it might be more severe, might be more frequent, greater amplitude. And so resilience helps to mitigate that. So the lower the resilience, the more extreme the impact of these various different perturbations. Greater resilience has a greater mitigating impact. Now, you can never get rid of perturbation entirely. So, for example, if there's a huge weather event on a regional level, it's going to perturb the system. The question is to what degree. And the more resilient the system is, the less likely that perturbation is going to be to have a major impact on the system. And not just major impact, but the ability of the system to adapt, how long it's going to take for that system to bounce back. So, just for fun, I wanted to see how well this equation stacked up. This was the part of the project where I actually looked up all of the data. Some of it specifically, you know, it was out there listed. Other ones I had to make some approximations. But let's take a look at this. I was looking at the USA National Food System for 2023. We have 1.9 million farms, an average of 464 acres per farm. Productivity, 361,538 calories per acre per year. So, now let's look at perturbation. We have the inverse of the resilience times subsidies minus climate change minus recalls. Now, a lot of these figures are in dollars. You probably noticed that. That's just the kind of data that's available. However, it's pretty easy to convert that dollar amount to calories because we know how much each calorie is worth. In this case, it was 4 cents, right? So I just divided this perturbation by 4 cents. And then we've got imports and exports. Imports, $194 billion came into the system. 197 billion went out of the system. So in this case, resilience, which was the log of farms divided by the log of total nodes in the system, is 0.109. So the resilience coefficient is the inverse of this. And what did I end up with? Let's go back to the graph of the national nutritional requirements. That's this line right here. My estimate was 0.318 billion, which is right here. So we were producing more than we required. The actual amount, which was easy to figure out, you just looked it up, how many calories were in the, was up here. So, was I exactly right? No. However, and this is very important, I got the order of magnitude right. So, I'm counting this as more or less a win. So what are the conclusions? Well, we started this saying, was Jean-Martin Fortier right? All things being equal, I don't think it makes much of a difference. In fact, we get economies of scale when we get bigger farms. Now, thanks to technological innovation, you get more, and government support for these smaller farms, you're able to maintain more of an equilibrium, more of a balance. There's less change in the system, but if we continue on the trend line that we're on, I don't think there's going to be much change. Farming is one of those things where you get a lot of lifestyle farmers, so they like the idea of moving out to the country and starting a farm, and they want to make this sustainable. More power to them. Running a sustainable small-scale farm is incredibly difficult. So if they need help doing that, and if that's a big part of their community, more power to them. But does Fortier's hypothesis hold? Just strictly understood? Not necessarily. However, that's all things being equal. But all things aren't equal. We are seeing more and more perturbations on every level geographically. Let's look at that resilience coefficient again. The more farms we have in the system, the better our resilience coefficient, and the better able we are to respond to and adapt to perturbations in the system. And what is crucial to understand is those perturbations are increasing. Furthermore, you can't even predict past 20 years because of chaos. We just don't know what the food system is going to be like because so many of those perturbations are approaching chaos. It's just unpredictable. So you better hope that we have a very resilient system that will respond to that chaos. Furthermore, there is a more close coupling between those perturbations as the years goes on. So it will be less and less likely that we are able to say, okay, here's how much came out of the system because of climate change, here's how much came out of the system because of conflict, here's how much came out of the system because of economic shock, because suddenly they will all start to merge together in order to be one massive perturbation. Climate change will spur on conflict, conflict will spur on economic shock. It will be one big perturbation. And it will be harder and harder and harder to analyze on a systemic level. So I, for one, am happy that we have a resilient food system, and it is my hope that we will become more resilient through the support of small-scale farms, because while we may get gains from economies of scale, I'm pretty sure that those economies of scale will not offset the level of perturbation that we see. And as noted before, those perturbations are happening at every geographic scale, and the more connected every one of those geographies are, the more impact a shock anywhere else is going to have on a particular geography. So let's hope that we see a lot of resilience on every geographic scale in order to mitigate the effect of perturbation from outside of the system and perturbation within the system. That's all I have. Thank you.